Hi everyone, welcome to lesson 26 of the Advanced Higher Stats course. In this lesson, we will be looking at the population correlation coefficient. By the end of this lesson, you should be able to test the hypothesis that the population correlation coefficient is zero. Another way to say population correlation coefficient is by the variable rho. Now, what is rho? Rho is a true version of R. So what do I mean by that? Let's say x bar, for example. X bar is the sample mean, and mu is a true population mean. So from a sample, we could get the general male height to be, let's say, 5'7", but the true general male population height is 5'9". Similarly, R is the correlation coefficient we've gotten through our sample, and rho is the true correlation coefficient. So let's recap. What is R? R we calculate using our bivariate data sample, and it shows us if there's a correlation. And what this test does is that it tests is R significant enough based on the sample size and other factors for us to say there is a linear association. So some assumptions for this test are the variables are independent and they follow an approximately bivariate distribution. And if your test statistic is greater than a critical test statistic, then you would write there's evidence of a linear association between the variables. If not, then you would say there isn't enough evidence, whilst also mentioning the significance and everything like that. Let's move on to an example now. So the first thing we would do is write our hypothesis. H naught is rho is equal to 0, and H1 is rho is not equal to 0. So just like in lesson 25, where we looked at this formula and worked our way back the way, we need to use this formula now. And we work our way back. So n is just a sample size, and r. So for r, we go to page 5 and we get this formula here, sxy over the square root of s double x times s double y. Now, in lesson 16, we covered how to calculate these, so we'll skip on to that and then do the extra steps we need for this hypothesis test. Now we have calculated those values. So just to summarize, I found that sum of x squared, sum of y squared, and then sum of xy. Then using the formulas on page 4 of the data booklet, I found the values I need for r. So we write down the formula. R is equal to sxy, which is 25.5 over the square root of s double x, which is 17.5, times s double y, which is 37.5, and that gives us a value 0.9954. Now we have to do a t-test. This is a bit cluttered, so we'll move on to the next slide. Let's now calculate the test statistic. So we have all our values. We just need to use the formula. So t is equal to r, 0.9954, times the square root of n minus 2. So our n is our sample size, so n is equal to 6 here. 6 minus 2 over the square root of 1 minus r squared, so 0.9954 all squared. And that gives us 20.78. Let's calculate our critical test value, our critical t-value. And for that, we need our degrees of freedom, which is 5. And we're doing it, this is a two-tailed at 5%, so we'll be on this column here. So 5 degrees of freedom, we go here, it is 2.571. The critical value is 2.571. So in our conclusion, we can say that 20.78 is greater than the critical t-value. Therefore, sufficient evidence at 5% significance to suggest that there is a linear relationship between the variables. And that's basically it. So it's just two kind of added steps, which is finding the R value and then doing the test statistic and like comparison and analysis. Now you should be able to do a two-tailed hypothesis test that tests that the population correlation coefficient is 0, and you should be able to conclude from that test and also state the assumptions you've made.